Today's topic is about exploring its origins and the impact on human bodies, and don't forget to subscribe to the channel and press like and wait for the third part, and don't forget to watch the first part. First, space exploration. In 350 BC, the Greek philosopher Aristotle proposed that nature abhors a vacuum, and this principle became known as the horror vacua. This concept builds on an ontological argument made in the 5th century BC by the Greek philosopher Parmenides, who denied the possibility of a void in nature. On the basis of the idea that a void cannot exist, it has been widely believed in the West for many centuries that space cannot be empty. At the end of the 17th century, the French philosopher René Descartes said that space should be completely filled. There were several schools of thought in ancient China that were concerned with the nature of the sky, some of which carried an understanding similar to the modern concept. In the 2nd century AD, astronomer Zheng Heng stated that space is infinite and extended, and behind it is a certain mechanism with the sun and around it the stars. He mentioned in the remaining books of the Xuanye school that the sky as it has no end, and it is empty and devoid of matter. Likewise, the sun, the moon, and the rest of the groups that share with it of stars float in a space of emptiness, and movement still exists in it. The Italian scientist, Galileo Galilei, realized that air has mass, so it is also subject to Earth's gravity. And he proved in the year 1640 AD that the emerging force prevents the formation of a vacuum. However, the manufacture of a device that could produce vacuum was at the hands of his student, Evangelista Torricelli. In the year 1643 AD, this experiment produced the first mercury barometer, which caused a scientific stir in Europe. French mathematician Blaise Pascal argued that if a column of mercury is supported by air, it is axiomatic that the column will be shorter at higher altitudes where the atmospheric pressure is lower. In the year 1648 AD, his brother-in-law, Florine Perrier, repeated the experiment on the Bay de Dome mountain in central France, and found that the length of the pole was 3 inches shorter. This decrease in atmospheric pressure was further illustrated by the experiment of lifting a half-filled balloon to the top of a mountain. As the balloon gradually inflated as it rose and was deflated as it descended. The original Dragonfly's balloon that was used to demonstrate Otto von Guericke's pump. In the year 1650, the German scientist Otto von Guericke made the first air pump, a device capable of refuting the principle of fear of empty space. Otto made a correct observation, which is that the Earth's atmosphere surrounds it like a crust, with a density that decreases gradually with height, which led him to the conclusion that between the Earth and the Moon is a void. In the 15th century, the German theologian Nicolaus Cosinus hypothesized that the universe lacked a center and a circumference. He believed that the universe, despite being limited, cannot be considered limited due to its lack of limits to contain it. These ideas have led to assumptions such as the hypothesis of the infinite dimension of space of the Italian philosopher Giordano Bruno in the 16th century, who expanded on Copernican heliocentric cosmology to the concept of an unlimited universe filled with a substance called ether, a substance that is irresistible to the movements of celestial bodies. The English philosopher William Gilbert came to a similar conclusion, claiming that the reason we can see stars is only because they are surrounded by a light ether or vacuum. This concept of the ether was developed by ancient Greek philosophers, including Aristotle, who conceived of the ether as the medium through which the celestial bodies move. The concept of a universe filled with a luminous ether was popular among some scientists until the early 20th century. This ether was considered necessary for the transmission of light through space. In 1887, Albert Michelson and Edward Morley conducted an experiment that is considered one of the most important in the field of physics, as it is considered one of the first strong evidences against the ether theory, which includes the movement of the Earth through a medium with consideration of the change in the speed of light coming from the Sun depending on the direction of the Earth's movement. It was not easy, as there was a mistake in this theory that led to its abandonment to another theory that appeared after that, which is the theory of relativity, by Albert Einstein, which states that the speed of light in a vacuum is a specific number that does not change and is completely independent of the movement of the observer or his frame. Reference. The English astronomer Thomas Digges was the first professional to support the theory of the infinity of the universe in 1576 AD, but the measurement of the universe remained unknown until 1838 AD. When the German astronomer, Friedrich Bessel, was able to implement the first successful measurement by measuring the distance to a neighboring star, where he measured the position of the star, Hen 61, and compared its measurement at that time to the current value, the position differs by only 0.31 arcseconds. This corresponds to a distance of more than 10 light-years. The American astronomer Edwin Hubble determined the distance from the Andromeda Galaxy in 1923 AD, using a new technique discovered by Henrietta Leavitt, which required measuring the brightness of the Cepheid variable in that galaxy. This resulted in the conclusion that the Andromeda Galaxy and all galaxies lie outside the Milky Way and are very far from it. The first to estimate the temperature of outer space was the Swiss physicist Charles-Édouard Guillaume in 1896. He estimated the cosmic temperature between 5 and 6 Kelvin by estimating the background radiation of stars. In 1926, the English scientist Arthur Stanley Eddington made similar calculations to the conclusion that the temperature of the universe is 3.18. In 1933, the German scientist Erich Regner relied on the total measurement of cosmic radiation energy to reach the conclusion that the temperature of the universe is 2.8 Kelvin. The modern concept of outer space is based on the cosmological theory known as the Big Bang, put forward by the Belgian physicist Georges Lemaitre in 1931. This theory says that the visible universe originated from highly compressed matter, and it is undergoing a continuous expansion phase. The matter left over from the beginning of the expansion underwent an internal gravitational collapse that produced stars, galaxies, and other astronomical objects, leaving behind a great void known today as outer space. Since light has a finite speed, this theory constrains the size of the immediate observable universe. This leaves the field open to debate as to whether the universe is finite or infinite. The term outer space appeared for the first time in the year 1842 in the poem, The Maiden of Moscow, by the English poet, Mrs. Emmeline Stuart Wortley, and was used as a term in astronomy by Alexander von Humboldt in the year 1845 AD. The term spread after the writings of H. G. Wells in 1901. But the shorter term, space, is older and denotes the outer sphere of the globe used by John Milton in his book The Lost Earth in 1667. Secondly, the Earth and its condition. Outer space is nature's closest example to absolute emptiness, where there is no friction, allowing stars, planets and moons to rotate freely in their orbits. However, even the deep space between galaxies is not devoid of matter, with every cubic meter containing a few hydrogen atoms. For comparison, every cubic meter of air we breathe contains approximately 1,025 molecules. The small density of matter in outer space allows electromagnetic radiation to travel very long distances without being scattered. And the average free path of a photon in intergalactic space is estimated at 1,023 kilometers or 10 billion light-years. However, extinction, that is, the absorption and scattering of photons by dust and gases, is one of the most important factors in galactic and intergalactic astronomy. Stars, planets, and moons retain their atmospheres by gravitational force. There are no clear and defined boundaries for the atmosphere and its different layers. The density of the atmosphere gradually decreases as we move away from the surface of the particle, planet, moon, star, and fades away until it is completely absent and equal to the surrounding environment. Atmospheric pressure drops to about 3.2 x 102 Pa at 100 kilometers above the Earth's surface, compared to 100 kPa for the IUPAC definition of typical atmospheric pressure. For altitudes above this level, the gas pressure becomes insignificant compared to the radiation pressure of the Sun and the kinetic pressure of solar storms. The thermosphere in this area has a lot of variation in the amount of pressure, temperature, and composition. These measurements vary greatly due to changing weather in outer space. The temperature on Earth is determined by the kinetic activity of the surrounding atmosphere. But the temperature in a vacuum cannot be measured in this way. So the temperature is determined by radiometry. The visible universe is filled with photons from the Big Bang known as the cosmic microwave background, and possibly a large number of correspondingly large numbers of neutrinos called the cosmic neutrino background. The black body temperature of the background radiation is currently 3 K, minus 270 C. 454F. Some regions of outer space may contain highly energetic particles with a temperature higher than the cosmic microwave background, such as the Sun's corona, which ranges between 1.2 and 2.6 million K. With the exception of a protective atmosphere and magnetic field, there are few obstacles to passing through space for energetic subatomic particles, otherwise known as cosmic rays. These particles have energies ranging from approximately 106 electron volts to 1020 electron volts for very high energy cosmic rays. The peak of the cosmic radiation flux is at approximately 109 MeV, which is made up of 87% protons, 12% helium nuclei, and 1% heavier nuclei. At higher energy levels, the flow of electrons is, roughly speaking, only 1% that of protons. Cosmic rays can damage electronic components and pose a threat to the health of space travelers. For some astronauts, like Don Pettit, space smells like metallic fire like arc welding. Despite the harsh conditions of the space environment, many forms of life have existed that can live in space for long periods. The lichen plants studied by the European Space Research Station were able to survive for 10 days in outer space in 2007. B. Arabidus thaliana and tobacco were also able to germinate after being placed in space for a year and a half. The hypothesis of mass scattering assumes that the rocks that travel space may have carried living organisms from living planets to other planets with an environment suitable for the development of life in the solar system. There is also a great possibility of life moving between planet Earth and the planets Mars and Venus. Effect on human bodies. Sudden exposure to low pressure, such as during rapid decompression, can cause pulmonary decompression due to the large difference in pressure inside and outside the chest. Even if the victim's airways are fully open, airflow through the trachea may be too slow to prevent explosion. Rapid decompression can burst the sinuses and eardrums, in addition to bruising and leakage of blood into the soft tissues. And the shock may cause an increase in oxygen consumption, which will lead to hypoxia. As a result of rapid decompression, blood oxygen empties into the lungs to equalize the low partial pressure. As soon as the deoxygenated blood reaches the brain, the human being, and even the animal, loses consciousness within a few seconds and then dies a few minutes later as a result of the lack of oxygen reaching the brain. The steam resulting from this condition doubles the volume of the body and slows down the blood circulation. But the pores of the blood vessels and their ability to expand prevent it from rupturing. The ability of blood vessels to contain pressure slows the process of bubble formation, keeping some of the blood liquid. Swelling and blisters can be contained with a spacesuit. Astronauts wear these suits, which are flexible garments equipped to relieve external pressure and protect the body from bubbling up to 2 kPa. In outer space, at an altitude of 8 kilometers, the suit is needed to provide the body with oxygen to breathe and prevent fluid loss. While the suit becomes necessary at an altitude of about 20 kilometers in order to prevent bubbling. Most of these suits use about 30 to 39 kilopascals of pure oxygen, just like on Earth. This pressure is high enough to prevent bubbling. But blood evaporation can cause nausea with a rapid drop in pressure and air embolism. Because humans are designed to live within Earth's gravity, it has been shown that exposure to a state of weightlessness can negatively affect one's health. Initially, more than 50% of astronauts suffered from motion sickness, which causes nausea, vomiting, dizziness, headache, lethargy, and malaise. The duration of these symptoms varies from person to person, but they usually last from 1 to 3 days, after which the body gets used to the new environment and all symptoms disappear. Exposure to weightlessness for long periods leads to muscle atrophy and skeletal deterioration or osteoporosis in astronauts. These symptoms can be minimized by practicing a regimen of exercise. Other effects or symptoms include redistribution or retention of fluids in the body, slowing down of the cardiovascular system, decreased red blood cell production, balance disorders and a weakened immune system. The other less visible symptoms: loss of body mass, nasal congestion, sleep disturbance, and facial swelling. Radiation poses a threat to human health, especially when exposure to various sources of radiation increases, such as high-energy radiation or ionizing cosmic rays, as it may cause fatigue, nausea, and vomiting. It also destroys the immune system and changes the level of white blood cells, as in long-term space travel. One of the symptoms of space travel for too long is an increased risk of cancer, as well as damage to the eyes, nervous system, lungs, and gastrointestinal tract. The body may traverse the 3-year round trip to Mars for high-energy nuclei, causing ion damage to cells. Fortunately, most of these particles are weakened by the spacecraft's aluminum walls and can also be reduced by water containers and other barriers. But the effect of cosmic rays on the spacecraft's shield produces additional rays that can negatively affect the crew. Therefore, more research will be needed to assess radiation risks and determine the necessary precautionary measures. Please appreciate my effort by subscribing to the channel. Click like. And wait for the third part.